Thanks, Terrell, and hello, everyone. I hope all of you are doing fine, and there is a lot of things going on out there. And yeah, so about our introduction, me and Archit are a part of Circuit Quantum Research, and we'll talk about Circuit Quantum Research and what it is exactly, and then we'll come on to today's topic, that is searching in the classical world using quantum spectacles. So this topic, as you can see from as you can maybe predict from the title, is not exactly related to only quantum stuff. There is quantum and classical, both things going on here. So briefly, let me just introduce all of us. So Circuit Quantum Research, we four, that is myself, Archit, and Aditya and Nishant. We four are the managing team for Circuit Quantum Research. And currently, there are about 20 people, 20 of us in this particular organization. And we focus towards spreading awareness and knowledge about quantum computing and related concepts. And we actually aspire to promote research among various young minds from high school or undergrads or whatever to take up research in quantum computing and develop viable solutions to real world problems. And currently we are taking up some of these topics, mainly quantum algorithms, QML, and quantum optimization. And in the near future, we have some plans to go ahead and take up quantum cryptography and some theoretical aspects of quantum hardware, because hardware is not that much accessible to everyone right now. And also to make that hardware, the lack of hardware, something is which is not very good. So to fill that gap, we actually aim to use all these open source quantum computing tools. So it's like we don't believe in reinventing the wheel. So we also try to use all these open source quantum computing tools like IBM Qiskit, Cirq, TensorFlow Quantum, D-Waves has their own SDK, Ocean SDK, etc. And yeah, we try to build something new out of using all these open source tools. So today's talk will be handled by myself and my colleague Archit. So I am the founder and senior researcher at Circuit Quantum Research. And currently I am pursuing my bachelor's in computer science. I'm a final year student, and I'm interested in quantum hardware, optimization, and quantum cryptography. Talking about Archit, he is the senior researcher at Circuit Quantum Research. And he is also a final year bachelor student from electronics and instrumentation. And his interests are gravitational wave astronomy and quantum hardware generally. So yeah, with that, I think let's get on to today's topic.
Quick question, Abeer, if I may.
Yeah.
So where are you located physically?
Currently, we are located at Bangalore, India. Yeah.
So you're 9.5 hours plus from the East Coast.
Yes. Yeah.
And
so
so when you talk about training and that sort of thing, that's one of the things I pay attention to closely, just before you get started. What's your scope on that? What's your vision? Is that focusing on India or Middle East and parts of Asia? What's your thinking on that?
Currently the quantum community is something which is like a very niche area. So that's why we want to focus a bit more towards research aspect, but we are open to any area. It's not restricted to any area. And also the lockdown and all these the situation regarding the COVID, everything has become online. So I think that will be a great resource, because what will happen, this makes us more connected online, And I think people would be able to contribute even if they are not present physically there. So yeah, we focus more on online training and online research and collaboration. And,
Okay, thank you.
yeah, no problem. So yeah, uh, yeah, let's get on to today's topic, that is searching in the classical world using quantum spectacles. And just to give a brief overview, we'll be focusing on three things related to a quantum algorithm, which is Grover's search algorithm. Okay, so Grover's search algorithm, then a problem of colliding blocks, and a problem of n-coupled pendulums. So yeah, let's get on to it. So just before we move on to the actual algorithm, just a brief overview of why these quantum systems are different from our classical computers. So the first thing is the phenomenon of superposition. So superposition was something which was which was presented in a thought experiment by Erwin Schrödinger. And this basically said that if there is a box, and if there is a cat inside the box with a vial of poison, which is triggered randomly by the decay of a particular radioactive element. So because this radioactive element decay is something which is random and cannot be predicted, therefore if the decay happens, then the poison vial will explode, and the cat will be dead. Otherwise, the cat will be alive. So we can't actually say when this particular atom will decay, and that's why the cat was said to be in a superposition of both dead and alive. And this is not this cannot be seen in such big creatures or objects such as a cat, but it can be seen in very elementary particles like electrons and various other elementary particles. So all these effects are seen at those scales, that is quantum scales, and not not on a bigger scale. But the cat's example was just taken to portray the idea of it. Second thing is entanglement, and entanglement is something which is like what Einstein termed as the spooky action at a distance. I'm sorry, I think someone is annotating on the screen. Okay, so entanglement was termed by Einstein as spooky action at a distance, and this particular thing was something which was considered as that it breaks the laws of physics, but it's nothing like that. It's actually not something like transfer of information instantaneously, but there is a lot of research done on to actually see entanglement, and for that fact, you can actually see this picture. So this particular picture is actually a real photo of entanglement between two electrons, and this was, I think, captured in 2018, if I'm not wrong. And this is a very special photo because this is the first picture that was clicked for entanglement. And finally, the third thing is interference. So interference is a property by which we can converge to some particular solution. For example, I have a classical computer. If we have some problem and there is a set of solutions, we need to determine which of them is correct and which of them is wrong. So a classical computer would have to go through each path individually and then try it. Whereas a quantum computer, because it has superposition and entanglement inside it, it can exist in all the states at the same instant of time, and then converge to a single state by using this phenomenon of interference. And that is something which makes a quantum computer so much powerful and more efficient than a classical computer for certain sets of problems. And mostly we'll be seeing the problems related to searching algorithms here today. So let's get on to that. But before we go to the quantum search, let's brush up our basics with the classical search algorithms. So generally there are two very popular searching algorithms. One is linear search. This is basically like you have an element that you have to search within a data set or database, or let's take an array for now. Let's say we are searching for 27 in this example, and linear search is something which is just seeing each element one by one and then comparing it whether that element is basically equal to my key element or the marked state which I want to finally retrieve from the set. So this takes about 10 steps in this particular thing, and it's pretty inefficient because for each element you are doing this comparison operation, and that is pretty costly. So that's why there exists another class of searching algorithm known as binary search. And how we do it is we take this array and we basically arrange it in such a way that it makes a binary tree. And this binary tree has the following properties. So the left node is smaller than the root node and the right node is greater than the root node. And this gives a very good data structure for searching operations, because what we can do with this is that we can search in a particular array very easily, and you can see it just takes 3 steps to get to 27 finally, whereas in the linear search it takes 10 steps. So in general, linear search is slow. Then the time complexity of linear search is on the order of n. So if there are n elements in the array, the average time complexity would be n by 2, so it is on the order of n. And one more thing what we can notice is because each and every element is being compared, we can actually have any kind of array. It doesn't need to be a sorted array. So in this example, it's a sorted array, but it's not necessary that we take a sorted array every time. Okay. So it can handle any type of input. Whereas a binary search is fast. Okay. That is a pro for the binary search. Time complexity is also better. It is O of log n, because here each level of the tree is where we are searching. So for example, I am starting to search here, then I search here, and here. So this particular thing will be in terms of log, the base 2 of n, because this is a binary tree. If it is a ternary or a quaternary tree, then this base will change and it will be much, much faster. And the next thing is sort of like a con, but the input cannot be any type of input. You always need a sorted array in this case, because if it is not sorted, then I'll have random values. So let's say 21, here in this case it's 14 and 28. But let's say if both of them were exchanged, okay, so this 14 and 28 were exchanged, and this now becomes an unsorted array. So now 28 will come here and 14 will come here, and this now no more follows that property of the left node being the smaller one and right node being the greater one, and thus it basically violates the particular property of binary search, which makes it more efficient. That's why for an unsorted or unstructured database, we need to finally use linear search itself. Okay, there are many more algorithms for searching, but for now I'll be focusing on only these two. So one question which comes up in our mind is that, okay, so for an unsorted database, the best case that I can get is O of n. Okay, but can I do something better than this? And this is where the quantum solution comes into picture. That is Grover's search algorithm. So Grover's search algorithm, it's just a brief overview. I think most of you might be knowing, at least on the surface level thing, what exactly Grover's search algorithm does. So yeah, let's get on to it. So the quantum circuit of Grover's search looks something like this. So we initialize the qubits, and we have two registers here. So the first register is where our elements of the array will be there, from which we have to search. Okay, And the second one is basically an ancilla qubit. Okay, so this ancilla qubit is used for something known as phase kickback. I'll get to that in the next slides. Then since we need to initialize the array, so the best initialization would be that all the possible states that this array can represent, let's take an equal superposition of that particular thing. So we initialize it using Hadamard gates, and then we do something known as an oracle function. So this oracle, what it actually does is that it selects a particular key value or a marked state and just operates on that, and the other states are unaffected. So I'll be telling how this works in the next slide. And the next step is then the Grover diffuser function. So this diffuser function actually sort of does the implementation of a reflection operation, and we'll get to that how this works. And then this whole thing is repeated O of square root of n times. Square root of n, that means we are getting a bit better complexity, right? A bit better time complexity here. Our linear search was O of n. Here it is big O of square root of n. So let's see how this happens. So step one, we implement all the Hadamard gates and we get an equal superposition of all the states. Okay. So this can be written as 1 by 2 to the power n, and then 0, 0, 0, then up to 1, 1, 1. Okay, it depends on number of qubits also. So this is the state that I have got after implementing the Hadamard gate, and it looks something like this. So if we just plot the amplitude of each state, it will look something like this, and each state will have an amplitude of 1 by 2 root 2 if I take 3 qubits. So for 3 qubit states, it's 1 by 2 root 2. The next step is implementation of the oracle function. So this oracle function is designed in such a way that it basically implements this particular function where it's fx equal to 0 for when this particular x is not equal to some marked state u. Okay, so we're trying to find u, the state u in this case. So if it is this x is not equal to u, then it returns 0. Otherwise, it returns 1 when x is equal to u. And this q is our ancilla qubit, and it is initialized in the minus state. So 0 minus 1 divided by root 2, which is the minus state. Okay, and this is how the oracle is implemented. So we have so when the oracle is implemented, it is basically fx xor 0 minus fx xor 1 and under root 2. And this x is basically, it's controlled using the x. So we saw a controlled operation here. So this is the oracle function that we are doing. And this is some computation that we need to perform in order to make this oracle work. Okay, so we compute it, then we put the oracle, and then we uncompute it. So that's what happens. So now, when this function is implemented, if my fx is 1, that means my x state, which I'm inputting, is equal to u state that I want to find. For that particular case, it basically phases the whole system by 180 degrees. That's why it acquires this negative sign. And if fx is 0, that means my x is not equal to the state u. Then it doesn't phase, and there is no change in the state of the whole system. And this is something known as phase kickback. The motive of this talk is not to go deep into phase kickback and all the intricacies of Grover's algorithm. So I would encourage you to look it up if you are not comfortable with the basics. Yeah. And we can visualize this in such a way. So we have all the amplitudes, and only the amplitude of the marked state which we want to find. In this case, it was 0, 1, 1. This has flipped to minus 1 by 2 root 2 instead of 1 by 2 root 2 in the previous step that we saw. Okay, and one more thing that it does is that it changes um, the overall average of the amplitudes. Okay, so now the average decreases. Earlier the average was about this, okay, about this line, that is the top of the amplitudes. Now the average has decreased because of this particular phase flip. Okay, so the decreased, we get a decreased average. And in the next step, that is step 3, we implement a Grover diffusing function. So the diffuser actually acts in such a way that it reflects the particular amplitude of the marked state about the average value of all the amplitudes. So this was the average value. So instead of reflecting it about this axis, it will actually reflect it about this particular average value. So let's see how that happens. And there is a bit of mathematics involved in this. And when we implement this operator, it basically calculates this average value and then does a reflection about the average of all the of the marked state. And finally, we get something like this, where the probability or the amplitude of our marked state has increased, okay, and the rest of the amplitudes have decreased, whereas the average remains constant. Okay, so why all these amplitudes have decreased is because of the property that the summation of all the amplitudes, let's take alpha I as the amplitude. Okay, the square of summation of I'm sorry, the summation of this particular thing, alpha I whole square, should be equal to 1. Okay, so this is the normalization condition that we generally follow, and that's why these amplitudes decrease and the amplitude of the marked state increases. This is one of the other representation that we can do. So one representation was this, where we show the amplitudes for each state. Another representation is something known as the phase diagram. So here omega is our marked state, and this omega is basically orthogonal to all the other states omega prime, which is so omega is the marked state. In the previous case it was 0, 1, 1. Okay, and all the other states, that is 0, 0, 0 and 0, 0, 1, etc., are this omega prime. And we take this vector S, which is basically an equal superposition of all the states, and when we plot it against omega and omega prime, we actually get something like this. So this particular state is our initial state. Okay, and this basically means that the cos theta by 2 value is the amplitude of all the other states, whereas the sine theta by 2 value is the amplitude of the omega state. Now, when we implement the oracle function, so here oracle is u omega. So when we implement this u omega function, it basically does a reflection about this omega prime axis, and we get the same angle. So if this is theta by 2, this will also be theta by 2, and we get this particular state. So only the amplitude of the omega state has, so it was positive here, let's say some positive amplitude. Now that has become some negative amplitude. Okay. Then after the oracle function, we implement the diffuser operation. So that is US. So we implement US on the state S. It gives us this this particular state, which is the reflection about the S axis, or the S vector in this case. So this was theta angle. So that's why this particular vector will have theta angle with respect to the S vector. So what we can see this that every iteration now, if I again implement an oracle function on this particular state, it will get reflected about this axis, and it will be let's say it will be reflected, and it will be somewhere here. The screen is not sufficient to go that far, but I think you get my point. And then the US operation again, which is the diffuser operation, will again reflect by this particular axis, and it will be somewhere here. Okay, so this somewhere here. Yeah, so this particular vector gets closer and closer now to the omega state. And every time it goes closer, it goes by theta degrees. So that's how we can say that we are reaching the correct solution with the help of Grover's algorithm. So a few takeaways or a few observations that we see from this particular thing is that the wave function always stays real. Okay, why this is the case is because you saw in the amplitudes also, these amplitudes never go to the imaginary part, they always stay real. Okay, so one of the observations is this, that the wave function always stays real. Second observation that we can make is that this basically relies on a number of reflections and let's say oscillations. Okay, so this can be represented as a phase diagram. So this phase diagram can correspond to some kind of oscillation system, some kind of oscillatory systems. Okay, and this reflection can be seen as an oscillation about different axes or vectors. The next thing that can be noticed is that the probability remains conserved. That means if the probability of the marked state increases, then the probability of the other states decreases in order to compensate for that particular thing. The next thing is that these operators US and UW actually don't commute. That means if I were to implement, let's say I implement U omega and then US on S, this won't give me the correct answer. This will be something else. Okay, so they don't commute. And another observation is that alternate US and U omega operations are applied to this particular state in order to get to that particular probability. Okay. Just for fun, this is an implementation of Grover's algorithm in Qiskit, and it uses 5 qubits. So you can see that it starts from the 0 state. So this is where it starts, and then equal superposition, and then there are a series of US and U omega operations. So here U omega is termed as UF instead of U omega, but it is actually the same operation. So a series of US and U omega operations are then applied, and finally the marked state probability increases to 100%, and we get a result. So yeah, this is basically the end of Grover's algorithm, an overview of Grover's algorithm. And now actually I would ask if there are any questions. I would love to take some questions at this point. Hello.
We're here. Anybody? I mean, you're explaining it quite succinctly, honestly. My questions personally are always towards the dreaded oracle, but I'll just leave that for the side right now. Anybody? Comments, questions? Looks like we're good, Abeer.
Okay.
Thank you.
Yeah. So I'll move on to the next part. That is classical analogs of Grover's search, which is the main topic of today's talk. So what I mean by classical analog is that I'm not implementing Grover's search in a classical system, but the mathematics which is used in Grover's search is very much similar to something like a classical system with some kind of oscillations. Okay, so for this talk, we mostly will be focusing on two of the classical analogs. The first one is the problem of a block collision. Okay, so there are two blocks, and there are collisions, elastic collisions between those blocks, and we'll see how this is very special problem and how this can be related to Grover's search. And then, by the way, it is also known as bouncing billiards problem, if you know it by that name. And another problem is the problem of n-coupled pendulums, and this will be taken by my colleague Archit. So yeah, let's get on to the problems. The first one is block collision problem. And how it starts is something like this. You have two blocks. The mass of one block is m2 and the mass of the other block is m1. And the velocity of the smaller block is v1 equal to 0. That means it has no velocity. And the velocity of the bigger block is v2. Okay, so it is moving with some velocity in this particular direction. So what will happen is that this block moves and then finally collides with this particular block. So after collision, the velocity v2 changes to something v2 prime. The mass remains constant, of course, and v1 changes to v1 prime instead of 0, and the mass remains m1. So the red block finally attains a velocity which is again same as the velocity of the blue block. Then the red block traverses some distance and reaches this particular wall, which is a rigid wall, and we are considering that it undergoes elastic collision always. So this is not a real example always. For real example, we might need to take some kind of coefficient for like making it an inelastic collision. For this example, we take that it has an elastic collision. So when this collides, the velocity v1 is actually reversed, and now the velocity is minus v1 in the opposite direction, that is in the opposite direction of where it started. And this problem is actually very special because what it does is it brings out a very special number. And that number, you might be familiar with this problem maybe, but I think I'll just maybe if someone knows, I would love to hear from you. If someone knows what gives us.
Yeah, we get the pi as the number.
Okay. Okay. So we get pi in only certain cases. So here I've taken general masses m1 and m2, but we get pi in only certain cases, and it's actually portrayed in really well in this particular paper from G. Galperin, and it's a paper from 2003. So it's a pretty old paper, but this gives an idea of how these two blocks come up with the value of pi. Okay, and this only happens in certain cases, and we'll discuss when that happens. So in this paper, going through this paper, you actually get to the result that if we finally keep the mass of the first block m1 as 1 and the mass of the block m2 as m, the number of collisions that the system will, so the number of collisions I'm counting, so I'm counting both the collisions, that is collision of the two blocks as well as collision with this particular wall. Okay, so the number of collisions will be this particular value, which is the floor function of pi of under root the mass of the second block. Okay, it's actually m2 by m1. Okay, but because we have taken m1 as 1, so that thing goes away, and we finally get pi under root m as the expression for number of collisions. Okay, so now I think someone here said that we get pi in this case. So can you guess what will be the value of m here now to get pi? It has to be some multiple of some power of 100. Okay, because 100 under root 100 will give us 10. Okay, and then we can get the digits of pi, or maybe if there is 10,000, under root of that will give us 100. Okay, so it'll basically one by one give the digits of pi, and we can very clearly see this in an example that I wanted to show. So maybe I'll share my whole screen. Just a sec. I'm sorry for the. Yeah, if someone can tell me if my screen is visible. It's coding.
Yeah, it's visible.
Yeah. Thank you. So we see that the mass of the small block is 1 and the larger block is 100, and we get 31. Okay, let's try with mass equal to the 1 and 10,000, and we get something like this. We get 3, 1, and let's just wait for this block to collide to the wall. Yeah, it's 314. Now, if we increase the mass further, we get more and more digits corresponding to pi. So we get 3141 in this case, and let's take a pretty large number, and this particular arrangement gives us 3141592, which is basically the digits of pi. We are getting digits of pi in this problem. So that's the classical problem that people have been like very much enthusiastic about. Okay, so the number of collisions is actually giving us the digits of pi. Okay, so these give us the digits of pi. Now, how can we see this in terms of the mathematical concepts related to Grover's search? Let's find that out. So we need to make a few assumptions first. So let's assume that we have a set of n blocks. Okay, so we have a set of n blocks, each with same mass, m. Okay, these are n blocks, n. Each has a mass equal to m. And we also define the problem statement that we need to find the kinetic energy of one of these blocks, okay, in some particular special setting that we are going to do. Okay, and for that particular setting, what I'm going to do is that one particular block for which I want to find the kinetic energy, I take that and I keep it separate. Okay, now I'm left with just n minus 1 blocks. Okay, and I take all these blocks and I melt them. These are metal blocks. I melt them and I fuse them together. I merge them and form a bigger block with mass m. Okay, so this mass m will be nothing but n minus 1, because each block has a small m mass, which is 1 unit, and there are n minus 1 such blocks. So the mass of the block will be n minus 1 units. Okay, and we also consider one thing, that each of these blocks have some particular velocity with which they are traveling, okay, in some particular direction. So velocity of each block is something like this. This I have written in Dirac notation, but as we know that the Qiskit notation is nothing, just a vector, or a vector in Hilbert space. So I can very easily convert it to something like a three-dimensional vector with I cap, j cap, and k cap, and I can write it as v equal to some v1 vector plus v2 vector, and so on up to vn vector. Okay, so this basically represents the state for different velocities of each block. Okay, so there are n blocks and there are n velocities. In the beginning, they will all be equal velocities. And the next thing is, of course, this thing. So m equal to n minus 1. So we take all the n minus 1 blocks for which we don't want to find the kinetic energy, and we take them together and form a particular bigger mass known as capital M, and it has the value of n minus 1. The next thing is, what we see is that the energy of the whole system is still conserved, because we have actually not modified any of the mass or the velocities of the whole system. We have just combined some of the masses together in order to make a particular set of them together. Okay, so the conservation of energy still holds here. And what this tells us is that the total momentum will always be like in some particular bounds, and it looks something like this. Okay, so you have only heavy ball, if it has only heavy ball is moving, then it will be this particular state. If only the lighter ball or maybe the lighter block is moving, then it will only be this state. And if both have equal velocities, then it will be something like this, because it's a superposition. So all of them have equal velocities. It's an equal superposition. So it will have this particular vector. So these two are orthogonal, and this particular vector represents the system, the information of the whole system. And this particular vector basically tells us that the total momentum will always be zero. Okay. Yeah. So this particular system now looks very similar to something like the Grover search phase diagram that we saw. So we had the omega state and the omega prime state. Okay, so here it is mentioned by S bar, but we can also write it as omega prime, because what is this? This is basically all the other n-1 blocks which are not in consideration for the kinetic energy problem. Okay, so once we make this particular system, you can see some similarities in this, and we can see that the kinetic energy of the lighter block is basically analogous to the omega state in Grover's search, which is the marked state that we want to find. So marked state. The second thing that we notice is that both of the blocks, that is the small and the big block, okay, the small and the big block, have equal velocities. Okay, so when they have equal velocities, this is actually represented by this particular thing. That means my state is in actually an equal superposition of those velocities. Okay, so when I apply Hadamard gate to my Grover search algorithm, it gives me this particular distribution, and that's why I can say that this is analogous to the S state here. Then if we see the kinetic energy of the heavy block, this is analogous to the S bar state, which was the omega prime state when we took the example of Grover's search. Okay, and this particular thing is analogous to this. Then also the order of collision matters. So if I have, I hope this particular block system is visible. So I have smaller block here and a bigger block. If my smaller block goes and collides with the bigger block, it won't make any difference, because there won't be any more collisions after that. Okay, maybe at most 2 collisions, because the block hits here and then reflects and then hits the wall, and then yeah. So this way it won't work. Okay, so that's why our operators, this collision order matters, and this is similar to that the operators of the Grover search, that is US and U omega, do not commute. Okay, so this is the particular similarity that we see. Then the mass of the bigger block, that is the n-1, that is n-1 units, is corresponding to the n-1 wrong answers in the Grover search algorithm. Okay, going further, we have this particular thing where both the blocks collide with each other, and this can be termed as the operator US. Okay, so this US operator, why am I saying this as the US operator? Because this block is going with some velocity in this direction, and then when it collides with this block, we can take this particular interface as the average value. So we had the concept of average amplitudes there. So the average amplitude actually decreases when the marked state is flipped, and the decreasing of that amplitude, the average amplitude, is shown by the block, the heavier block, like it's moving in the same direction even after multiple collisions with this red block, until finally the direction reverses. So that is analogous to the US operator. The collision with the wall is analogous to the U omega operator. That means the reflection about the omega prime axis. Okay. So the omega prime axis reflection about this particular axis is analogous to this because this is a fixed wall. This is not moving anywhere. Then we have small ball. We have the small block which is bouncing back and forth. So it's going back and forth in these directions, and is analogous to the alternate US and U omega operators. Then the velocity of the ith block is the amplitude. Let's say not Vi. This should be alpha I. Amplitude alpha I of the ith eigenstate, and 2 times the kinetic energy of the ith billiard or the block is actually analogous to the probability of the ith eigenstate, because kinetic energy is actually proportional to velocity square. Okay, so if velocity is amplitude, then kinetic energy should be probability. Then finally we have a few more. So the conservation of kinetic energy is conservation of probability. Conservation of phase space, that means we saw this particular phase diagram, and it never goes out of this phase diagram. That means the phase space is conserved. That is relatable to the unitarity of the whole system of Grover's search and overall in quantum computation. Then the motion is purely horizontal. That means it doesn't go in any other axis. It doesn't move in any other axis or any other direction. This is analogous to that the wave function of the whole system is always real. It doesn't go into the imaginary subspace. And then the collision order. Okay, so yeah, this is repeated. Final thing is that a number of collisions here is given by floor function of pi under root m, whereas the number of repetitions are given by this particular formula, which is actually a simplification of something like this. It is actually pi by 4 times sine inverse of 1 by n. Yeah, I think it's under root 1 by n. Yeah. So it's a simplification of this, because if n is pretty large, then 1 by n will be very small. And we know that if theta is small, then sine theta is almost equal to theta. So sine inverse theta can be just written as pi by 4 times under root n. And these are the number of repetitions that we need to do in Grover's search algorithm. And that's how we can say that a classical process, which is actually nowhere related to something like quantum mechanics, is mathematically very analogous to the Grover's search algorithm. And it's very beautiful to see that we can actually find out these kind of analogies in our particular classical world. And the paper that was referred for this particular thing was this particular paper, which is playing pool with psi. Okay, and it's known as the bouncing billiards problem. You can search it up. And there are many YouTubers that have made videos on the collision of blocks to get pi problem. There is 3 blue 1 brown. There is coding train. Yeah, so you can check that out. But yeah, this paper is really good to explain the concepts what we discussed today here. And just one quick extra thing, that is the factor of 4. So we can see that there is an extra factor of 4 which comes here. So why does this come? Why does this factor of 4 arise in our particular equation, the number of for the number of repetitions? And that is because of 2 reasons. It's actually not a factor of 4. It's basically 2 factors of 2. Okay. So the first reason is that in the collisions problem, we are counting each collision. Okay. So here each collision is counted. Whereas in Grover's search, only if we implement the oracle and then we implement the diffuser operation, this whole thing is considered as 1 repetition. So that's why. So here there are 2 collisions, whereas here there is only one repetition in that time. So 1 factor of 2 comes from there. So that's why we need to divide by 2 once. The other thing is that there is a difference in stopping point in both things. So in the collisions problem, the system starts somewhere here. Okay, this is the bigger block and this is the smaller block, and it goes with the velocity here. And finally, the final system, the final state of the system would be that uh, the kinetic energy which was transferred to the small block by this bigger block is then finally completely transferred back to the bigger block again. Okay, so now the direction of the bigger block would be opposite. So that means we are actually finding the kinetic energy and then again losing the information of kinetic energy to make this particular thing go in reverse direction. Okay. Whereas in Grover's search, what happens once we find the omega state, okay, this omega state, we start from this particular S state. Okay, and once we finally find this particular omega state, let's say I found out this particular omega state, and this S vector actually just coincides with my omega vector after some operations that I do for Oracle and diffusing operations. We stop there. Okay, we don't go back. I mean, we don't keep continuing in this direction, or we don't go back here. Okay, so that is the difference in stopping point. So in Grover's search, it actually stops at theta by 2. It actually stops at theta equal to pi by 2. There is a slight of error. That's why I wrote approximate. And the block collision stops at theta approximately equal to pi. So we have this particular diagram explaining that. And you can see it starts from the S state. The Grover search stops here, whereas the method mentioned by Galperin for this particular problem, it stops somewhere here. Okay, so between minus S bar and minus S, it stops somewhere in this region. And whereas the Grover search stops somewhere in this region. So this stopping point variation is the reason for the another factor of 2 that we have in this particular case. So yeah, I think yeah, if there are any questions, I would like to answer those at this point of time, and then we'll move on to the next problem by Archit.
I have a question. Thank you thank you for the explanation so far. I haven't read this paper. I'm curious if there is if this analogy continues with how if you go over, root n iterations, Grover's will, the angle starts going back the other way. And I'm just curious, is that would that be like having a wall on the other side of the block, large block?
Actually, that would be analogous to. So as I told that we have the initial state of the system where the bigger block is moving in this direction, and the smaller block is stationary, and then finally there is an intermediate state where the bigger block finally stops moving. The velocity of bigger block V2 is 0. And the smaller block has maximum kinetic energy, right? So if this was proper Grover search, we would have just stopped on this particular state that the smaller block has the maximum kinetic energy, and the velocity or the kinetic energy of the bigger block is 0. So I think you're asking that if we continue the repetitions of Grover's algorithm even after this particular number, then what will happen is that again you reach the omega state, okay, and then you continue further from there. So it would be something like losing the information that you have. So you got some particular information. So your initial state was this, that is equal superposition. And then you did some transformations on this to change the information of the state vector and finally get to the marked state omega. And once you again continue in the other direction, you're again losing the information of whatever the search algorithm that you have done. And that's why this repetition is very specific. It's very important that you stop after these many iterations. Otherwise, it will just go ahead and it won't make any sense, because the probabilities again will start to equalize, and when it finally reaches somewhere here, let's say in the Grover search, it will be somewhat similar to this particular S state, but just that the amplitudes of the other states will have changed. So the amplitude of the omega state will remain same, whereas the amplitudes of other states will have reversed. Something like this would be the case now. So your omega state will be like this, and the other states would be having the same amplitude as omega, and they will be in the negative direction. So yeah, that would be an analogy, maybe. I hope I answered your question.
Abeer, I have a question.
Yeah.
So, yeah, are there any algorithms that are built on top of Grover's search, with a similar architecture that give a better time complexity or space complexity?
As of time complexity, I don't think there are. The best time complexity is still O of under root n, big O of under root
Right.
n. But there are some algorithms like, so you can use Grover's search to solve some particular problems. For example, there is a satisfiability problem, or what we call it as SAT problems. Okay, so satisfiability problems can be solved using Grover's search, and it's much more efficient as compared to the conventional classical methods that we use to solve these kind of problems. So satisfiability problems is one of the things. Another thing is so in communication, in security aspect, actually, let's say generally we use the AES 128 standard for encryption. Okay, but this particular thing is not quantum safe. Okay, so what we mean by quantum safe is that any quantum algorithm cannot break this particular thing in a given time. Okay, like at least it takes a very long time, that means. Okay, so if we take AES 128, we know that there is a set of numbers from 0 to 2 to the power 128 minus 1. Okay, so between this range, I have there is some key value that I need to decrypt my message. So if, let's say, an attacker, if an attacker wants to attack my system, what they can do, they can run Grover's search using a quantum computer on this particular 128 qubit set. Okay, so they just need 128 qubits, and they can find the key in big O of under root n, that is under root 128, that is about O of 64. Okay, and that basically boils down to having just 64 bits for my security purpose. And 64 bits is not a very good level of security. Like NSA actually recommends at least greater than 80 bits for any key. Okay, so Grover search, what it actually does, it basically reduces the security factor by a factor of by a factor of half. I'm not sure if factor is the right word, but like basically, if I have taken n bits, it makes it equivalent to n to the power 1 by 2, that is under root n. Okay, so that's why generally now the standard which we are using is AES 256, because AES 256 means it is basically 256 to the power half, that is 128. Sorry. Yeah. So I'm sorry for such a haphazard writing, but yeah. So it basically makes it equal to 128 bit key size. Okay. So this then makes it quantum safe. So there are some applications like this. There are some not very famous applications for Grover search, but mainly Grover search actually can be used in a lot of things. And another parameter of Grover search that we discussed today was this, that is the amplitude amplification. That means it basically amplifies the amplitude of the marked state. So this amplitude amplification also can be used at many places. And yeah, this particular thing, like not only for searching, you can use amplitude amplification for like all these SAT problems and AES, like breaking AES and cryptographic hash problems, etc. So yeah.
Thank you.
Are there any more questions? If not, I think we'll move on to Archit's presentation here.
Great.
Yeah.
Thank you.
So Archit, I request you to present your screen. I'll just stop sharing.
Yes. Thank you for first of all, I would like to thank all of you and would like to greet from my side for coming over here. And I hope that you all are safe in these difficult times. And a special thanks to Terrell for giving us such wonderful opportunity to present. So quickly, without taking time, I would start off with the topic. So just a quick checkup, is my screen visible?
Yes.
So Abeer has given a really intuitive and nice explanation of what Grover's search algorithm is, what it does, and extending the the topic of today's presentation. So the second topic is an n-coupled pendulum problem. So it is on the same lines, like there is no Grover search directly involved into this problem, but the mathematics is the same that goes into it. So coming on coming to the topic, so the word pendulum, so like quickly clearing out the basics. So a pendulum is just a bob of mass, like which is hung from a hinge, and it is let free to oscillate on its own. So in this slide, what we see is that the previous animation has been broken up into few basic basic physics equations, and what we actually are seeing over here. So I'll quickly, oh wait, sorry. Yeah. So what we are seeing over here is that this equation gives us that what is the total the resonant frequency of the natural frequency of the pendulum of how it oscillates, and it gives us this differential equation. And finally, while having an approximation over the sine theta term, like taking really less values of sine theta, we come over to this equation of the natural frequency. So coming to the next slide. So now I'll try to just build few basics of the things that are going to come up in the next few minutes. And so what we are seeing over here is that if I try to explain it in a really quick manner, so we are seeing that the shorter length pendulum is having a higher frequency, and the longer length pendulum is having a lower frequency of oscillation. So given the initial conditions and the length, so this is kind of an observation that we can make from this information. So yes, so now we come up with the actual problem statement. So what this problem or the research paper that is at its heart wants to explain is that, so there is this support pendulum, and it is having an n pendulums which are coupled to this support pendulum. So what is happening what is happening in this problem is that we have one pendulum, so which is of a shorter length. So out of n pendulums, we have this one little pendulum which is of a shorter length, and all these pendulums are of the same length and same mass. So like similar to like what happens in a Grover's search algorithm is we have an unstructured like search data set. We try to find out one specific number that is of our interest. So here, this is the same like that number that we are interested in finding, but this is not a number. This is a pendulum in itself that we are trying to get a hold of. So what actually happens is we take the help of a phenomenon named as amplitude amplification. And this is one of the key like principles of Grover's search algorithm. And what is happen, like why is it more significant in this? Because if say suppose we let this whole system to like, if we want to classically find like which pendulum is this, so we like we try to calculate, like we search it, like we go once over here, we say, oh no, it is not the pendulum, then we go again, we say, oh no, this is not the pendulum, and so on. Like we move further until we finally reach out to this. So the time taken for this whole thing is in the order of like big O of n. So what actually happens like in this algorithm is if we let this whole setup to run for O of under root n time steps. So what actually happens is the energy like that is flowing like that is going down from the support pendulum to these coupled pendulums. So the amplitude of I'll quickly change the color. So the amplitude of this particular pendulum so amplitude of this particular pendulum starts to increase, and then it becomes easier for us to find like which pendulum is of our interest, and which is like or which is the odd one out from this lot. So quickly erase and moving on to the next slide quickly. So yeah. So now like a bit mathematical part comes into picture. So what we are doing in this first equation is that we are like making a Lagrangian equation of the setup that we had in the previous slide. So we had a support pendulum and we had n pendulums with one pendulum which was odd one out. So like the upper pendulum has mass m and a length l, and the pendulums in the lower part have a mass of small m and l, but the pendulum which is odd one out has a mass of m1. The mass is m by n, and the length of this pendulum is L1. So what this equation is actually depicting is that x like x is the displacement of the support pendulum, and the equations that are following it. So x1 is the like amplitude displacement of the defective pendulum, and the xj term that we are seeing over here gives like are the displacement of the jth pendulum, if we want to show. So this Lagrangian equation actually has like the necessary information about this particular system that we are having. So so K in this equation, the capital K in this equation is actually denoting this term. So the authors in this paper, like I'll come to which paper, so it is a suspense. It will be revealed at the end. So what the authors wanted to try is that they just like rather than simplifying this Lagrangian equation and then moving forward with the equations, they left it like in this generic form, so that the transformation from this mechanical like system to say some electrical system, because if we are doing some control system analysis of the stability of a particular system, then there we have the electrical counterpart also there and the mechanical counterpart, and we want to check the stability of both the systems. So there the conversions to solve the matrix equations become more of a prominence. And this equation being a really complex equation, so the authors wanted to keep this as generic as possible, so the conversions from a mechanical system say to an electrical system becomes easier, like it's more feasible. So yeah, that was for the introduction, like just explaining the things. So now now we come to the next step of the equation. So here what we do is that so we have this like we assign a variable y across the mass mode of the whole system, and this actually is done to simplify the equation, so that it becomes more feasible for the upcoming for getting to the solution. So the terms over here and here are same, but there is like a slight difference in this term. So this term actually is being split up into the two terms, and there is a change of base is not a correct word, but I'll use it right now. So like the iterating variable actually changes, and the up till the summation which is done is also changes, and this particular variable of y comes into picture. So if we closely look, so the y terms are isolated over here, and all the terms containing x and the required information that we have are isolated in this portion. So like why this this isolation is more of a significance over here is because like separating this y variables, which are not more of a necessity for the solution of the equation, helps us to initialize y to be 0, because it won't have any such effect on the whole system overall, and helps us to focus more on this particular equation. So moving forward with the slide. So, clear it. So as I said that because we don't have we don't have the significance of y as such, so we initialize it as 0, and we omit omitting few of the O of 1 over square root of n terms, which are not of our interest. We arrive at this equation. So this is the reduced Lagrangian equation, and it is containing all the necessary information which are of our interest. So we quickly separate this particular variable and assign it to epsilon. And what is happening right now over here is that we have two particular like degrees of freedom which are strongly coupled to each other. So they are like namely x and x. There it is. Yeah, x and x dash. So these are the two degrees of freedom which are strongly coupled together, and they like the third variable of epsilon is not too strongly coupled. So like like if we solve for the first two like strongly coupled degrees of uh, freedom, so we actually get two modes of frequencies which are omega 1 and omega 2. So this diagram actually is explaining what these statements are saying, and that the natural frequencies that correspond to the special pendulum, so the shorter pendulum that we were having, the natural frequencies which are corresponding to it would be will be omega, which will be equal to square root of k1 upon m1. So this is how the breakup is actually happening, and like so now we move forward to the next slide. Yeah. So now a bit of mathematics come into play. Okay, a bit more mathematics come into play, I'll say. So what we're having is that the previous Lagrangian equation that we were having. So now we are actually reducing it into the equation of motion. So like and doing like reducing it into a matrix form, so that we have more tools available for its analysis and like doing more operations on it. So like the this the M like indicates the is the mass matrix of the whole system, and the X is like the displacement vector, which is having these three like degrees of freedom that we were talking about, out of which these two are like strongly coupled, and this is the corresponding to the special pendulum that we were talking about. This is the mass matrix that is like for the Holland. So this is the support pendulum mass. This is the like n-1 pendulums that were normal, and this is the special pendulum that we were having, the mass of the special pendulum. So, and this is the stiffness matrix. Like so, this is like the stiffness matrix, and this. So we are finding the x vector, and we actually like after arriving to this equation, we like solve this like by assuming the time dependencies of the xt, and we assume that xt x of t is time dependent on e raised to the power I of rho of t. So this rho factor, like doing a straightforward like more analysis on this factor, we have this rho square term, and the eigenvalues of the rho squared like term is given by this lambda matrix. So this lambda matrix is looks something this. So it is having the inverse squared of inverse squared like m matrix to the power of minus half. Then we have this stiffness matrix, and then again the mass matrix raised to the power of minus half. So we get to this particular matrix, and this particular matrix is like having few special terms. So this omega c matrix is the like coupling degree of like frequency of coupling degree, and it is denoted by this, like it is having these terms in it. Then then we have this omega power minus 2 term. So it is the frequency of the center of mass mode. So the center of mass mode that we were talking about initially, where we defined the y term and also that is the omega squared minus 2 terms which represent, and the omega squared term that we have over here. So it represents the k1 the frequency of the deviating pendulum. So the pendulum which is I'll say the shorter one. So it depicts that. So quickly moving to the next slide. Yeah. So what we like come across is that after like solving the lambda matrix that we had, so we and so like getting the eigenvalues of the previous lambda matrix. So as I said that the omega like 1 and omega 2 are the frequencies which were being like uh, I'll say derived from the X matrix and the X bar matrix. So because these were like together like highly coupled and from there we get like in this 1-2 subblock. So we get this these as the corresponding eigenvalues. So from here like we start to get like the values of the frequencies that we want to look into, and like then again like doing like adding the third mode of operations and to the matrix lambda, like the which was the less significant mode that we were having. So like we get like we get to this matrix, and this matrix is like after this transformation, like the lambda dash matrix will like is of the like more is of more significance for us, because it helps us to like analyze the things more properly. So if we go to the next slide. So, so up till now, what we have found is that we have done like a thorough analysis of the frequencies of the like of the pendulums, and we arrived. So we arrived to a particular result stating that okay, this is the eigen values and the values of the frequencies that we might have. So what actually happens is like is of a more significance for us. So we try to find that particular like pendulum that was of our specific interest. So because like initially we were given the n pendulums, and so we had n, and like say so like now talking a bit more in a generalistic way. So what happens is that, say, out of the n pendulums present, we have say suppose q pendulums, like which were like belonging to the these pendulum that were like the shorter pendulum region. So the problem same estimates in this o of q time complexity, and like since the this was the like um, a classical way of finding. So now what happens is that like the probability of getting the shorter pendulum like probability of getting encountered to any one of the shorter pendulums like it will be q. So it will take 1 by like o of 1 or 1 by q like time like samples before like we get to one of like single occurrence of a shorter pendulum. So what we like what we find that because it is taking the O1 cycle to estimate the oscillation frequency of the pendulum. So it will take O of 1 upon Q cycle to actually derive any reasonable estimation of Q. So now what we are converging to is the fact that now we are going to estimate the proper value, like the value of Q, actually like finding how many pendulums are there, like which are of a short length. So I'll quickly give a significance of this. So like help here. So the big question comes like, why even bother about about this problem? So as Abeer also like rightly pointed out, many like uses where the Grover's search algorithm can be used, and in the encryption methods and various places. So it becomes like a really integrated part for the finance industry and other places too, where from a particular like say a data set, we need to find out certain like things, and we need to segment them and classify them, and we need to do an analysis on the data. So there like this finding the element problem comes. So why I said in the initial slides, like, it is a general like thing that we are looking for, is because of this its versatility, like that I am talking about right now. So we just talked the versatility from a pendulum to the scaled up to a finance area. So now quickly moving to the next points. So we up till now we have like it's like estimated like it will take some O of 1 upon Q like 1 upon root Q time steps like cycles to be able to derive any reasonable like value of Q. So we have that like in the previous section, that the techniques that we had it is we found that it is possible to get the estimate of Q, or the particular pendulum that we wanted to see, like in only like O of root of n time cycle. So the like the strength of this coupling like happens to become O of Q, and this causes, so initially, as I told, that it is a say an amplitude amplification problem. So here like you can see what that particular thing means. So it says that the strength of this coupling is O of root of Q. So what this actually causes is that the energy from the coupled pendulum, so energy like goes down, and it actually flows back and forth in this particular, the pendulums that are short, and it actually amplifies the pendulum like the amplitude of the pendulum, because of the energy like resonating back and forth in this thing in the shorter pendulums. So like we have the pendulums with a periodicity of uh, so the periodicity of the pendulum is of 1 upon root Q cycles, and because the energy like flows back and forth between these pendulums, so the amplitude for the O of 1 over root of Q like cycles will be observed in a cyclic variation. Like, so we'll be able to clearly see that which pendulum is behaving differently from the other pendulums that we have. So this like the length of the cycle. So say suppose that this is the shorter pendulum that we are analyzing, and we like it is, the energy is moving back and forth in it, and its amplitude is increasing in the time step. So the way its amplitude like increase in the cyclic variation, so the length of the cycle, say the length of the cycle comes out to t. So this t actually will give us an estimate of the number of pendulums like which are the culprit, I'll say. Like we'll be able to find the culprit pendulums or the shorter pendulums in the array of n coupled pendulums. So this is what the whole paper was about. And as I said, so at the end I'll talk about the paper. So it's like just like after this I'll try to give one more like an analogy, like a shorter brief description. So this was the paper which was forming the heart of this particular problem statement. and its name is Classical Analog of Quantum Search, and it has been written by Grover himself along with Anirvan and Sengupta. So this is a really nice paper, and I'll like um, appreciate, and I'll say like everyone who is present here and every enthusiast will like just go through the paper. Yes. And quickly, I'll take just a few minutes of time to show one more uh, analogy. So I'll share my screen. Yeah. Just a quick like follow up. Is my screen visible?
Yes, Archit.
Okay. Okay. So I hope that you are seeing my OneNote screen, and yeah. So what this whole like small blog is about. So the things that we have gone through in the past few minutes, like few 20 minutes, is actually having a really weird significance, and it is having a really weird like uh, I'll say connection to a totally different like field. So we in the previous section we saw the n-coupled pendulum problem. So we here have just the three coupled pendulum. So I'll quickly do this yellow color as mine. No, I'll take the red color. So this three-way coupled pendulum problem. So what it does, so I'll just, so it is having three resonant natural frequencies of operation. And like what happens is that there is a really interesting state named as the neutrino frequency state. And that happens to be achieved when the middle pendulum is disturbed, and it is either sent into oscillation, and the resulting like oscillation that we have of the whole system is named as the neutrino frequency. So why is it named as a neutrino frequency? Because in the quantum domain we have the like we have probabilities of the states that we are having. So the probability where it is like the amplitude, the probability are like the major I'll say properties that we are like looking into, and the same thing is happening over here. So the amplitude with which so these three pendulums like um, will go into motion. So once this middle pendulum is set into motion, when all the three are in rest, so this pendulum like the amplitudes with which these three pendulums are oscillating is giving us an information about the the electron neutrino, the muon neutrino, and the tau neutrino. So this is another analogy and a really deep mathematical analogy that has been formulated. And what we see over here is that for the for the electron neutrino, we have this probability of finding the electron neutrino in the process that we are interested in. We have this probability of getting the muon neutrino, and we have this probability of getting the tau neutrino. So like how these neutrino come into picture is that they are formed in a process like in the core of the like sun that we have. And it is really interesting that these neutrino take like a really long time to actually reach the surface of the sun. And I'm not sure about the time range, but it is like somewhere ranging from 10,000 years to say somewhere 100,000 or a million years too, because they randomly move around in the sun's inner core, and like it takes them time because of collisions happening. And once they reach the surface, so they are set free to like go into their journey and reach Earth, reach to us. So once they like arrive on Earth, so what scientists do actually is that they try to like find what are the probabilities of getting these neutrinos, and they do this in like huge laboratories. So the same analogy is fine in this kind of setup. And when I'm talking about the amplitudes of these like pendulums, giving us information about the probabilities of a particular neutrino, it means that the process, so this is the process that we are talking right now. So this is the process, and this process has like emitted these three neutrinos, and probability of finding any specific flavor of the neutrino is like analogous to the amplitude of this particular pendulum, which corresponds to the electron neutrino, then the muon neutrino, and the tau neutrino. So yeah, like that was like the one quick weird thing that I wanted to like introduce you all to. And like it is not sad, it is really interesting and really intuitive to like see that, and like neutrinos are really hard to detect, but now scientists and everyone are like working on finding these neutrinos like via various projects and international science projects. So yeah, that was it from my side today, and
Okay,
I'll quickly stop sharing the screen.
great. Thank you, Abeer. Archit, thank you very much. Folks, we'll see you all next time. Appreciate it.
Thank you.
Thank you, Daryl.
And do
Thank you,
follow
everyone.
us on